Okay. So this is where we were. I don't know. I just creating problem. The connection is not good. Okay. So I'm just revising. I just wrote the proof where we got confused last time. Since we have already written more or less all the details. So I just written it just some time back, 1 hour back. So if you want to copy, you can copy, but it's all there already. But I'm just recalling. So suppose if we have a spectral measure P, which is defined from omega to okay, which is defined on a omega. It's not omega, it should be script f, I'm sorry. It is a script function defined on omega f is a measure space. We have a measurable space. Then we have a set function taking values in projections, which is called a spectral measure. Then we define df to be all those x with respect to which you have then given any x, you have a measure. You have a spectral measure. Given any x, you have a positive measure, finite positive measure. Then all those square integrable function is if all those x for which a function f is square integrable with respect to that x, okay, is the df. Okay, so where mu yx is defined like that. Then you define this tf from the domain df. Okay, and the definition is defined like that. We have seen that this defines a well-defined operator, unique well-defined operator. Okay. Then we proved that tf x square equal to, the norm of tf, norm of tf doesn't make sense. It's an unbounded operator. If it is bounded, then that's a different case. That will be same as I think the infinity norm. So tfx equal to this norm of tfx equal to the norm f square. It's written like this. Okay. Then we proved that tf star is equal to tf bar. So this implies star is always closed. So in particular, tf is equal to tf bar star. Okay, tf bar star, you can write it. Hence, tf is a closed operator. Okay. Then we were proving this, and there was some confusion, so I have written it again. So what we were trying to prove is, if f and g are bounded operators, oh my god, it's not. Is it because of that? No, the problem is somewhere else. So if f and g are bounded operators, then we know that TFTG, you just compose those operators, which is TFG. Okay, and I forgot to say, the TFG is contained in TFG. That's what. But when they are unbounded operators, when they are defined like that, f and g are not necessarily, of course, f is bounded function, then TF is a bounded operator. And f and g are unbounded operators, then the composition TFTG, which makes sense on a domain, which we have defined, okay, on some domain. So, and then TFTG is contained in TFG. Okay, and also we claim that the domain of TFTG is equal to DG, which is the domain of TG, intersection DFG, which is the domain of TFG, not TFTG. Okay, TFG. Okay. Okay, so we want to prove these two things. We want to prove three. Okay, we want to prove the last statement. TFTG is contained in TFG, and then we want to prove the domain matches with that. Okay. So for that, first we assume f is bounded.
Okay. The statement you were doing last time, it was domain of TFTG is equal to D, domain of G intersection domain of F.
Correct. I have written it.
But here it's domain of FG.
FG. What did I write? GF I wrote. GF does not make sense. DF and FG are same anyway. They are functions anyway, so it's okay. Whether I have written, might have written. Only TFTG, you shouldn't get confused. Functions you can multiply whichever the way you want. That's okay. TFG is same as TFGF. Functions are commutative. Yeah, FG. Just to keep it consistent, we write it DFG. Okay. Okay. So first we will prove this when F is bounded. Okay. And one thing is we will again and again apply this. I mean, by Fn, I always denote the truncation to n, which we have already defined. Okay. By always, we mean in the whole proof, we assume that Fn is equal to 1 mod f less than or equal to n. You hit it by this function times f. Okay. You call it Fn. And we will use it later. So for the time being, we will assume f is bounded, then we will apply for Fn and take limits. That's what you will do. Okay. So first assume f is bounded. In f is bounded, tf is a bounded operator. Okay. And for dg, so dfg is basically, I mean, the dg equal to, no? dfg is equal to dg, right? It's equal. It need not be even contained. They are equal, right? When which is bounded, f is bounded. Yeah, f is bounded. So when you apply TG, it's going to, I mean, you can apply TF, no problem. So DG is equal to DFG. Okay. And then for X in DG, okay, Y in H, we have this equation. Okay. What do you have this equation? That equation, you take the inner product with Y, TF TG X, but then TF is a bounded operator. So you can take it to the other side as TF bar, okay, because it's a bounded operator. And then you apply the definition of TG. Okay, that's the definition of TG, which is equal to integral G d mu TG Y TF bar YX, which is just the definition of TG. See, TG is defined like that, no? TF is defined like that. You can see TF is defined like that. So I'm just using the definition of TG. Okay. Here. Here. So this is just the definition of TF, TG. Okay. I'm applying to this Y, which is this vector, Y and this vector X. Okay. Here Y is TF bar Y, and this is equal to this. So this is just the definition of TG. Okay. That's what I'm applying. So then I got this. On the other hand, if you look at Y TFG X, which is equal to by definition FG d mu XY, which is also true. Okay. Then for bounded operators, when G is also bounded, when G is also, we are going to first see when G is also bounded, what happens. Then we want to see, take limits for G also. So I don't write all those details. When G is also bounded, then TFDG equal to TFG. Okay. So these two integrals, whatever they have integral, this integral and this integral. Okay. These two integral are equal when F and G are bounded. Okay. But then you can take limits. Then these two integral are limit for both F and G are bounded. Okay. Then if you take, you fix everything else, F is fixed everything else, then you can take G and converging to G, G and converging to G. Okay. Which is just, you take Lebesgue dominated convergence theorem. I mean, everything is, you justify that. So these two integrals are equal for a general G also. For bounded G, it's equal. So then for general G, these integrals are equal. See, we are just, this is the argument you should remember. We are applying the fact that TFTG equal to TFG when both F and G are bounded. These things we used earlier also. So the integrals are equal. Now I take the limit and these integrals are equal for any G also. Okay? Then we come to operators again. We are using LDCT and we got this. Now you come to what it means in terms of operators. In terms of operators, this just means, so you can just see TFGX equal to, you can just see what it means. TFTG at X is equal to, which is just T. Yeah, that is TFTG. We got one TFTG, we evaluated and we got it. This is TFG, we evaluated, which we got it. So the operators are also equal. Okay. For bounded, the operators are equal. So we have some integrals are equal. We take limits in the integral, which we can do by like dominated convergence theorem. You see, then we got an integral equation, two integrals are equal. That precisely means these two operators are equal at X. Okay. So we got this for X and for any G and bounded F. We are still assuming F is bounded. So that is why we have used that F is bounded. Okay, for X in DG and F is bounded. So this is true. So we have proved whatever I have just marked. So the star marked the star. We have proved that that equation holds for X in DG and F is bounded. And since we know that D of T of DG equal to DG, and the theorem is already true for bounded F. We have proved the theorem. Whatever we want to prove, we prove. Then F is bounded and G is anything. Okay. Now we want to remove the condition for G also. So now to prove for all F, we can consider, first of all, first we got this equation. For F bounded, we have this equation. We have already have T of TGX equal to T of GX. So we have this equation, right? We have this equation. T of TGX is equal to this, right? I mean, this is nothing but norm of TF of TGX, right? Square, right? By the definition. And this is not the norm of TFGX, norm F square, right? So these two are equal for F is bounded. So these two integral, again, we are using the same idea, we have to write it again and again. Again, we are using the same idea. This is equal to that operator. This is, so when F is bounded, these two norms are equal. That's what we have proved. So these integrals are equal for F is bounded. Now we will take again LDCT or monotone convergence theorem, whatever, and LDCT, we need LDCT because we have FG there. Okay. So again, these two integrals are equal for any F. Okay. So these two integrals are equal for any F. Okay. First, these two integrals are equal for bounded F because it satisfies that condition. I'm just taking, I mean, those two operators are equal. T of TG acting on X is T of GX. If you take norm square equal to norm square of that, you get this. These two integrals are equal for F bounded and G anything, and X is in the domain of G. Okay. Then you take limits. So this is true for all Fn. You take limits and you get that this is true for any F and any G. Now we have got it. Okay. Now what is the meaning of this? What is the meaning of this? The left-hand side says that, I mean, suppose the one of this side is, I mean, what do you want to prove? Suppose we want to prove that TF intersection TG, TF DG is equal to this. What is TF DG? It is all those X in DG. So you take X in DG, okay? Then TGX, the X in DG intersection, I mean, X is, what do we have this? Suppose if you have DG into something in DG intersection DFG, X is in DG intersection DFG, okay? Then X is in DFG means right hand side is finite, right? That's what it means. Okay, I'm not going through each and every statement, okay, but I'm saying it. Okay, I'm not writing each and every statement. Maybe I will write. Okay, maybe I will write. Okay. Oh. Yeah. See, first, what is it? Let us write. X is in DFG, okay, intersection DG. So X is in DFG means that the right hand side, RHS of star is finite, right? So the left hand side is also finite. This implies left hand side is also finite. That means TGX I mean, we are already having X is in DG. That means TGX is in DF. Okay. Which means, but X is already in DG also. So this implies X is in D of domain of TFDG. Domain of TFDG is all those X in DG such that DGX is in DF. Okay. So these things implies that this is contained in, this DFG is contained in domain of TFDG. Now we want to prove the other way. Okay. Now if it is the other way, now if X is in, conversely, if X is in domain of TFDG, that means X is in DG, that is X is in DG, and TGX is in DF, this implies LHS is finite. Okay. So the RHS is also finite. That precisely means that RHS is finite. Precisely means that X is in DFG. Okay. So that is a proof. This you should remember to, I mean, the meaning is exactly there. You should use the definition and you get this. That is the definition of something is in X is in DFG. And that is precisely, I mean, that's what it means. So this implies X is in DEG intersection DFG. Both are in DG. Whether they are in the domain of TFDG is what we verify. Okay. X is in DG, then it is in DFG, if and only if TGX is in DF. Okay. We use this star. I will send you these notes. Okay. By the PDF of this. So what do we have? So we have proved the domain statement. See, we have two statements. One is TFTG is contained in TFG. Okay. So this domain of the left-hand side should be contained in the domain of right-hand side. And when you restrict the right-hand side on the domain of left-hand side, it should coincide with the left-hand side. Okay. So that is one. So further, that means TFTGX equal to TFGX. That we have to prove for in general. Okay. So to prove that, then to prove for all F, TFN, TGX, I mean, this is to prove for all F, I mean, again, you take Fn such that TF, this is true for bounded Fn. We have already proved this TFTGX equal to TFGX equal to for, that is we have proved for bounded F. Okay. So it is true for any Fn, TFNX. Okay. Now we know we have already used this idea. What is that idea? We have this idea. If TFN, I mean, if X is in, I mean, we have already TG, we applied for this. See, we have proved that, I mean, we have earlier used something, no? If Fn T Fng minus TFG acting on X is actually equal to T Fng minus Fg. Right? Okay. So the norm square is also equal. So the corresponding integrals are also equal. So, but the left-hand side something else holds because Fn is bounded. Okay. So, I mean, shall I leave this as an exercise? We have already done this. We have gone through this idea earlier. Okay. If something is, if you have something is less than or equal to some integral, the integrals are equal, and then this this TFNG converges to TFG. Okay. So TFN, so the norm will converge to that. So the integral will converge, but the integrals are equal for all bounded operators. So from that, it will follow that TF, I mean, it also follow that TFNG, TGX also converges to TFGX. Okay, I leave it as an exercise. Just look at it. We have already used this. I have to use the same details exercise. Okay, please go through. That proves that TFTG is same as is contained in TFFG. And you have to use this in the proof of spectral theorem, which I have given it as an assignment. Okay. I send you this notes. Now I show you the spectral theorem. So spectral theorem says the following. P be any self-adjoint operator, then there exists a unique, that exponential mark is unique, a symbol for uniqueness. So there exists a unique spectral measure, okay, P from defined on the real line, which is actually defined on the spectrum of the spectrum is unbounded here. Unbounded operator, spectrum is unbounded, okay, which we haven't gone through. Those things, those details we haven't gone through, but it is on real line. That's what, because we want to take some inverse image, and so we haven't used the spectrum detail here. P from R to P of H, such that T equal to Tf naught, where F naught is just the identity function on the real. Okay, so this is a statement of spectral theorem. We want to use this. We want to use the spectral theorem for bounded operators, and using that we want to get this statement. Sketch.
Should it be from Borel subset of R?
You are exactly right. Yes. This bus. Yeah, it is from Borel subset of R. Okay. So sketch of the proof. More or less, I am giving you all the proof except the details you have to write. Okay. You take R is equal to T minus I inverse. And we have already proved that R is a bounded operator. Okay. And T is self-adjoint. So R is a normal operator. Okay. You have to see that R is a normal operator. That is what you have to do is you compute R star. R star equal to R star R. You have to check this. Okay. I mean, you have to check that R star is this. That you have to check. Okay. You can easily verify using inner product. Okay. Which will satisfy for all the elements. Okay. Using inner product, you have to go through just the definition, write out the definition and everything, and you will verify that R star is this. R star has a meaning, it's bounded operator. So using it for any xy, it should satisfy that inner product condition. So R star is equal to this.
Assignment, we should go through the whole thing.
Exactly. Rigorous proof is the assignment. Okay. That's all. Okay. This is sketch. So the details you should write. This self-adjoint, why this is star and all those things. Okay. T plus I inverse. And you have to verify that they commute. That also is not very difficult to verify. Okay. So R star equal to R star. So it's normal. Now, in spectral theorem, of course, you don't have to write the proof. So by you can just directly use spectral theorem of bounded normal operator T minus I inverse can be written as sigma of R, which is a spectrum of R. Okay. And is a DQ is there is a spectral measure. Q is a spectral measure. Now, Q is a spectral measure defined on Borel sigma of R sigma of T. Define now Q from R to see. I mean, this is defined on Borel sigma T. Now you define a new spectral measure on real line. Okay. BR from BR to range of Q. I write range of Q because I want it to be invertible. Okay. So then this map T to 1 minus T minus inverse, which is invertible. Okay. So you can, I mean, usually the measure is written in terms of something inverse of a function. But when it is a 1-1 function, you can write it like this. Okay. So P of E, you take the measure P of E, spectral measure P of E on the real line as Q of E of E. Okay. For E in B of R. So now use change of variable formula. Just change of variable formula. Just remember that, which we have gone through last time. So this integral is equal to that integral. Okay. Now itself intuitively it is clear that P gives the spectral measure we want for the operator, our operator, self-adjoint operator T. Okay. So for that you should remember one thing, that 1 minus T minus I. Okay. This is essentially bounded function. Why is it a bounded function? Because there exists a sigma R is compact. I is not in sigma of R. Okay. See, it's a compact set. So you need it to be compact. Then I is not in sigma of R. It should be sigma of R. I'm sorry. Okay. I is not in sigma of R. So there exists an open set around I such that U intersection sigma R is not equal to empty. Okay. This implies I near that. I mean T minus I. Wherever T minus I will be unbounded. I mean wherever it is going to be unbounded. So that means T minus I is less than epsilon, right? I mean, T minus I is very small. Okay. On that measure is 0. There is a measure is 0. So that function 1 by T minus I is bounded, essentially bounded. Essentially bounded means what? P is the measure. P such that T in R such that 1, I mean, there exists a M such that P of T such that 1 by T minus I mod of this is greater than M equal to 0. That is what it means by essentially bounded. You have to prove this.
Isn't T 1 by T minus I always less than or equal to 1 in small units?
1 by T minus I?
Is always less than or equal to 1 in small units.
Why?
Because P is real. So
T is real.
T minus I is greater than or equal to 1 in modulus.
T minus I is greater than or equal to 1 in modulus. Is that?
Yeah, because P is real. So it is T minus I greater than or equal to modulus of I.
Yeah, I think so. Right now.
Should be bounded.
Yeah, I think so. Yeah, T is then the real line. It will always be away from I, right? So where is it? This is essentially bounded. It is always bounded. T is not in I. I mean, yeah, there is always an open set which does not intersect with this, with the real line. So it should be always bounded. Yeah, why did I write it like that? Okay, maybe not needed. You just think about it, and then if you find a problem, you write it. Okay. Needed. Okay. Okay. Now you take S is equal to T dpt. We want to prove T equal to S. Okay. Then you prove first S minus I R equal to 1. Okay. And we know that range of H is equal to D of T. I mean, range of R of H is equal to range of R is D of T.
So it's because like
This is R operator.
R is not self-
R is not self-adjoint. So
yeah, so it won't always sigma of R won't turn the real line. It is from I is not in sigma of R in this form.
no, what is the problem? R is not in,
No,
but the integral is in real line, no?
No, like R itself is not I asked you the same thing last time.
R is not self-adjoint.
Yeah,
It's only
so
normal.
Sigma of R can be it can have complex numbers.
Correct. Yeah, it will have. Yeah.
Yeah, and that's why it's essentially bounded. That's what I mean.
No, but P you are integrating. See, the essentially bounded, why do we need? Yeah. We want to say, no. The point is, we want to say, see, that is the point. We want to say that,
He is in the spectrum of R.
no, what is the problem? P is,
We want P to be bounded, right? So
no, we don't want phi to be, there is no phi to be, we don't want that. No, wait a minute. Where are we using it is essentially bounded? T is essentially bounded. So 1 minus T minus I with respect to P is a bounded operator. That's what we want to say. No, what is the problem? Why are you saying?
okay.
1 minus T minus I with respect to P. So, we want to say that these integrals make sense and they are equal.
Yeah.
So 1 minus T minus I, this is a bounded, even though P is a spectral measure, not supported in a bounded set, which will not be supported in a bounded set. This is a bounded function. It will not be, it's a finite, finite means P of whole set is identity. Okay.
Yeah. No, like this 1 over T minus I is essentially bounded on sigma of R. That's all.
That is also true.
Yeah.
But we are not defining 1 minus T minus I on sigma of R.
Yeah.
We are defining it on real life. That's why. So you don't need that. Is correct. It's not defined on, it's defined on R. Okay. And it's a bounded function on R. So it will give bounded operators. Okay. So now you define S to be like that. You want to prove S is this. This is range of R. Is equal to range of R. Range of R is R of H is equal to D of T. So from that equation, conclude that D of T is contained in D of S. And also that T is equal to S. T is contained in S. That means, S restricted to domain of T is actually T itself. Okay, using that, whatever I have written the hint also. Then it's very easy. So, okay, write that. Now you take adjoint, justify that. That's all. Then they are equal. That's all. Okay. Okay. I need more time, so I will just leave this and then go to the next theorem. Okay. So this theorem I have to prove. I will take one more class. That will be a short class on Friday. It will be a very short class. Okay. I will just show you the momentum operator and then possibly uncertainty principle. Tomorrow there is a Gana. Tomorrow there is a Gana. Last class. At 6:30. Okay. So this is the Stone's theorem. We have already seen the statement. Okay. So the proof only I am going to give. Let H be a Hilbert space and P be a spectral measure. Then ut is e power minus itx. You can define for any function. So they are all bounded operators. Okay. Then this is a strongly continuous unitary group. That statement is clear. I don't have to prove anything. For each bounded function, this is a spectral measure. E power minus itx has modulus 1. It's a spectral measure. So you get this. And it's a unitary because u minus t is equal to ut minus t, which is u0, which is identity. They compute. We have proved that this is true, no? TG equal to TFG for bounded functions. Okay. Because of that, if you apply that, u minus t is equal to identity. Okay, so they are unitary. Okay, and they are unitary, and the us ut also you can just compose it, and you will see that you can compose it inside the integral. So which is us plus t, and everything follows from the spectral theorem. So that's first statement. There is nothing. Only strong continuity you have to see. Okay, proof. If ut equal to integral e power minus itx dpx, okay, whatever we have defined. So then we want to prove that strong continuity. Then utx, norm utx square is equal to integral utx minus ut naught. Say that tn converges to t. We want to say that tn converges to t, utn converges to ut. That's what we want to prove. So utnx minus utx. Okay. Square is equal to e power itnx. You can take it inside. I mean itnx minus e power minus itx norm square d mu xx. Just a finite measure. Xx, right? So there is something problem. There are 2x. So I have to use yes. Sorry. I have to change this. I will use yes inside. Okay. I mean, to distinguish between, or I will use xi here. I will use x. Since I have used in the statement, I don't want to change. I use x. Use xi here. Okay. So this is the statement we have. Okay. And is this over real line? And if Tn goes to 0, I mean, you know that whatever the integrand is bounded by 2 and which is finite measure, so it is integrable. So LDCT implies UTNX converts to UTX. Okay, so this is what, sorry, xi. This is what called strong continuity, of course. Lebesgue dominated convergence theorem says that. Okay, now we want to prove the converse. So given any, so the strong continuity is easy. Okay, just write the integral. Lebesgue dominated convergence theorem will be. Okay. So conversely, if you have a continuous unitary group, strongly continuous unitary group, okay, then there exists a spectral measure P, unique spectral measure P satisfies that star, that equation star, where ut is given by e power minus itx dpx. Okay. This theorem, the proof is in KRP's book. Even the unbounded operator theory is also in KRP's book. You can look at all that, but it's more detailed, more messy. Okay, so you can look at it. Okay. So what do you have? We have a, now you have a unitary group. Okay, it satisfies us plus t equal to us ut and it's strongly continuous. Then there exists a spectral measure corresponding to that. This theorem can be proved using Gelfand-Neymar theorem, which says that every commutative, you take the algebra generated by ut. That's a commutative sister algebra, and it contains identity. So it will be isomorphic to some continuous functions on something, c of x. Okay, and any representation of this continuous function, I mean, then this continuous function, but these are all represented. I mean, what I mean is any representation of continuous function is actually given by a measure mu. So you can pass on from here. You have a h, this algebra. I mean, the algebra generated by this. I mean, you take the C-star algebra or Van algebra generated by this. You take the algebra, C-star algebra or whatever generated by that. The ut, you take ut and take the, we need C-star algebra or Van algebra. We need Van algebra. Okay, so the Van algebra generated by ut, this will be contained in H. But then using this C of x, all those things, you can actually get, you will, if you see, go through the proof of spectral theorem, you will see this. Okay, you can actually get a map unitary from H to L2 of something, L2 of some measure space. Okay, and this ut, you will get it as e power itx. Okay, You can do that and you can get it. Or you can get the spectral measure using those. You can go pass it on to LT, then the same idea, whatever I'm going to use, will tell you that. But here in KRP's book, he uses something very nice. You don't need all those representation theory. You can use what is called Bochner's theorem in probability, which says that a Fourier transform of a measure determines the measure, which is true. If you have a function, and a nice function, then the Fourier transform determines that function. That's the theory. So that is true for any measure also. What is the Fourier transform of a measure? If you have a measure mu, so the converse. So for that, we want to use Bochner's theorem. Bochner's theorem says that if you have a measure mu, okay, defined on any measure space, mu on some omega, script f. This is the Bochner's theorem I'm recalling. Okay. Then you can define phi of t, okay, which is defined on R. Okay, real line. Phi of t is equal to integral e power minus itx. Minus itx. E power itx will also do, but we are taking minus itx. Then d mu. This should be a Borel measure on R. Measure on R. That can be defined for any R. So you take this phi of t, okay? Then phi of t satisfies this condition. This is phi of t is positive definite, which we have already defined, which I will recall again. Phi of t and phi of 0, mu is a probability measure. Otherwise, you have to use something else, okay? Mu probability measure. Okay. So phi of 0 equal to 1. Okay. It satisfies these things. Conversely, this is what is important. Conversely, so the converse statement is what? Conversely, if phi is a function, R from R to C, no? Phi is a function R to C, which satisfies phi is positive definite, phi of 0 equal to 1 and positive definite. Okay. Then there exists a unique probability measure on R, okay, such that this phi of t is equal to integral e power minus I tx dx. Okay. This is Bochner's theorem, okay, which is just the Fourier transform. Fourier transform is 1 somewhere, okay, for a nice functions. So this is what it's just the Fourier transform. E power minus I tx is Fourier transform. Okay. So Fourier transform of the measure determines that. Given anything which satisfies those positive definite conditions, there exists, which is like taking the inverse Fourier transform. You can actually get that measure using e power itx. You doing something, you can actually get that measure. Anyway, we will not do that. So this is Bochner's theorem. We are going to use this. Okay. So first assume, to prove Sloan's theorem, first assume what? Assume there exists a vector xi with a unit vector xi. We want probability measure, so we are taking unit vector xi with norm xi equal to 1 and ut xi that with t varying r, take this, is total in H. Okay. We assume this. This is what is called a cyclic vector. The vector, ut is a representation of R. Or you can take the C-star algebra, fundamental algebra, C-star algebra is enough, generated by ut. Okay. Then you apply that vector on xi, you get everything. That means this vector xi is cyclic. It's said to be cyclic for that. Okay. Let's not go into the terminology. So this is total in H. Okay, this is the condition. That is span closure is everything. It's total in H. Okay, then define phi of t equal to u ut u. Okay. For any t. So this is inner product. So you can see that then for T1 up to Tn in R, the alpha 1 up to alpha n in C. I'm checking the positive definite, which I have already defined when we consider tensor product and another thing, positive definite function. And the same definition, okay, the function. So the summation alpha I, alpha j bar, okay, ij equal to 1 to n. Phi of Ti minus Tj. Okay. This is equal to summation Ij equal to 1 to n. And maybe alpha I bar alpha ij, because we have the other way, no? So I write it like this, which is equal to alpha I bar alpha j. Phi of Ti minus Tj is going to be u Ti minus Tj, but which I write it as u Ti Tj minus Ti, maybe, to get it right. Okay. UTI star UTJ acting on you, right? Which I can write it like this. So these things will imply this is, I mean, we have already done this several times. This is going to be summation alpha I UTI U summation alpha j alpha j UTJ U, j equal to 1 to n, I equal to 1 to n. So this is greater than opposite. This is just the norm of that. This is greater than opposite. So the function is positive definite, and phi t of and we also have phi of 0, which is of course just did I use u? Sorry, it should be xi. That u should be xi. I'm sorry. Change everywhere. U to be xi. Now phi of 0 is just xi, which is equal to norm xi square equal to 1. Okay. Okay. So it satisfies Bochner's theorem. So there exists a measure. So there exists a probability measure mu on R such that integral over e power itx d mu is equal to phi of t. Okay. The integral is over x, t is fixed, okay, over R is equal to whatever. So there exists a unique measure, okay, which so that this is satisfied. Phi of t equal to this. Now it is just routine. What is it? Then define. So, oh my God. Try that. I'll just write it. We just try that. Define. It has come. Okay. Define a new operator V from H2. So we are using some more theorems, which I will not. What shall I do? I mean, if I write, okay. Define H to this L2 mu. Okay. As I said, we have to shift everything to L2 mu. Okay. We have defined V from L2 mu, which is defined as ut of, we have already got a vector xi. Ut xi is total for when you vary t. Okay. Ut xi will go to e power minus itx. That's all, the function. which is a function which is an L2 function. Okay. Notice that these functions, this e power itx with t in R, okay, is total in L2. To prove, if you take any bounded set, if you take a bounded compact set, so compact set in R, okay. So I will tell you the proof orally, which I stated in the Ghana class also. Some of this. You take any bounded set in R, okay, then e power itx, these kind of functions, span of these kind of functions, okay, span of these things. So that is dense in C of that compact. You take any compact set, then e power itx is dense in C of compact set in the uniform topology. Okay. Then on L2 of that set, C is dense there because uniform convergence imply L2 convergence. Okay. So C of any compact set is contained in L2 of that compact set. Where when measure can be any measure, doesn't matter. Okay. L2 of compact set because uniform convergence imply because of dominated convergence theorem, L2 convergence. So this implies this e power itx. I mean, when x, when t, I mean x is limited to bounded set, it is dense in the L2 of the bounded set. Now, by truncating that, you know that all bounded functions are, even simple functions are dense in L2. So because of that, these things are dense there. Okay, let us not go through the thing, but please accept it. This follows from Stone-Weierstrass theorem. Stone-Weierstrass theorem says that these kind of functions are dense in uniform topology in C of compact set, and compactly supported functions are dense in L2 of R, and LDCT, all those things, and CC of R is in L2 of R is dense. Okay, because of all these three statements, LDC, Stone-Weierstrass theorem, LDCT, and CC of R, which is compactly supported functions, are dense in L2 of R. Because of all these statements, these things are dense there. I mean, these things are total there. The span is dense there. So that is, so now you use the earlier theorem. UT xi to this, they are dense there. And also this is true that UT xi, US xi. Okay, this is equal to xi u s minus t xi. Oh my God. This is actually defined as P of s minus t, which is equal to integral e power I s minus t x d mu x, right? Okay, I'm sorry. I will write it, it will be clear. It may come anytime. Okay. So, moron, where in everything getting recorded. Oh, here also the screening stop. This I don't understand. When it stops there, here also it stops.
We should really not come back to this section.
Yeah, we should next lecture, if a short lecture, we'll go somewhere else. Okay. If the problem is with this, we will finish this now.
I don't know.
It came and went again. I mean, S minus T or T minus. Okay. So I have the following. So we have a map which is defined. B is a map which is defined from this set. Okay. UT xi to this function e power minus I t x. This function. I mean, I put a dot so that it's a function then. E power I t so t. These functions, okay, Now we know that this is total and that is total. We have already seen these functions are total in L2 This is total in L2 of R, L2 of mu in R, and this is total L in H. Okay. And we have to check the inner product, which is just UT xi and US xi. UT xi equal to US xi, which is same as xi U S minus T xi, which is equal to P of S minus T, which we have given here, which is equal to e power minus I integral S minus T d mu 6, which is equal to the inner product of this function e power minus IT ITx IT dot. Okay. Inner product of minus I S dot. The function where the dot, wherever dot is written, it's a function. It's a function. It is the inner product of L2 L2. Possibly there is a bar and everything. Yeah, it is here. It's bar here. There's no. So it preserves the inner product. So there exists a unitary operator. Unitary B, maybe call this B naught. Okay. B from H, and that is also total to L2. Okay. Now we just have to see that now E is a set in R. Okay. Then the measure is on R. Okay. Define P of E, which is a projection in P of H. Right, is equal to U star of U is from here. Sorry, it's B star of 1, not V star 1. I mean, we want to call it as a function, it projection. So 1E acts on as a multiplication operator. Make M1. Okay. Now U star B will land up there. You have B, you have a vector B, it will go there. You hit it by M1E, where M1E acting on F equal to 1E. This is an operator, a projection. L2. This is the projection in L2 view, and you bring back that projection by this unitary into this. Okay, and that is a spectral measure. This will be a spectral measure. That is clear. It will be additive because this is a very nice function. Nicest isomorphism is, isomorphism is not the isomorphism between Hilbert space. It's an isomorphism. It's a homomorphism of algebras, which is also linear, which preserves, which is continuous in any topology you can think of. Is this okay? P going to UP U star for any unitary. This will be the nicest homomorphism we can think about. And all continuous homomorphism on B of H will look like that. If you take phenomenal algebra and other thing, its case is different. Okay. So we have a spectral measure. We have brought it back and we got a spectral measure on H. So this is a spectral measure. Now all we have to see that our unitary looks like that. That's all. Okay. Now what is UT? Now UT acting on. You have to see what is not acting on side. Acting on any. You have to see that UT acting on US side. Right? We want to determine how UT looks like. Okay, with respect to that. Okay, so you have to verify how it looks on US side. These are total vectors, right? So now this is equal to UV of the multiplication by this function. There it will be multiplication by this function, which is e power minus IT, this function, times acting on multiplication of e power is dot, this function, right? This is just the vector. V xi will go to this function, e power minus is dot. This is function considered in L2. This is the function, there is an operator corresponding to that. Okay. It is this. I'm just wondering which property of the spectral integration I'm using. So then you just have to verify the following. Can't go to the other side. We have got a spectral measure on H. Okay. Then we want to talk about e power minus I e x d. This is what it is. We have got a spectral measure. P is a spectral measure on H. Okay. Now we want to see that ut has the spectral representation. That is, we want to see what is e power minus I t x d mu x is equal to, we want that to be which is just, this is equal to yx maybe equal to y to kx. This is what we want. Right? This means ut equal to that spectral integration. That's what we want. Okay, this is what we want. Now you just shall I leave it as an exercise? UTX, now we have, well, this is for all x. Now it is enough to verify this for a total set. Okay, and any total set will look like that. Okay, now you write this inner product and all that, change it, and it is satisfied here, you bring it back there. Okay, I leave this as an exercise. This is very easy exercise. You have to understand where anything maps. Okay, you can look at Square Facebook, this proof is there anyway. Okay, the same proof. Okay, so this implies proof when ut is total. This is total. Okay. Now you have to decompose. For the general case, so for general case, let H not equal to take the span closure of some UP set for some set. For some set. H. Okay. Now you have taken it like that. Now ut of H0 is contained in H0. That's clear. And ut star of H0 is also contained in H0. This implies ut of this is equal to u minus t, right? Ut star is u minus t, we checked. Okay. Ut of H0 is contained in the ut star of u is u minus t. Now so this implies ut of H0 per is also contained in H0 per. Okay. So ut leaves H0 and H0 per in it breaks into two things. So now you can, so for ut you can have this spectral measure. You have a spectral measure on H0. Now you have H0 per. That you have to again break it. Okay. Now you take, I mean, if you have one spectral measure on one Hilbert space, another spectral measure on another Hilbert space, you can just take the direct sum. I mean, if you have Xi1 to P1, okay, from H1, so from R to H1, okay, and you have P2 from R to P of H2, okay, then you can define P from R to H1 direct sum H2. Okay, by, I mean, you can take any number of direct sum, countable direct sum also. Right? Because these are all projections. So if it is a projection here, if you add it like this, to the projection again. That's that P of P equal to P1E direct sum P2E. These are also a spectral measure. Okay, P of the whole set is 1, direct sum 1 is 1. Okay, so it's a, so you can take any direct sum. So now I mean this proof is clear now. Now you take collection of all sets, which for such that the collection of all Hilbert spaces, such that this they are each one of them is left invariant by this UT. Okay, and which is a collection which satisfies the axioms of Zorn's lemma. So there will be a maximal element. That should be everything. Otherwise, you take the perp and something like this. So it's a maximal element. So because of that, you will get a sequence. So there exists right side I equal to possibly infinity countable direct sum such that direct sum hi equal to h and each u restricted to ut, okay, restricted to hi is cyclic. Direction is cyclic vector. That is direct is xi in hi such that u key xi equal to hi. Okay. And it leaves everything invariant and okay. Now you take the direct sum of all those spectral measure, you get a spectral measure, and each one of them it is e power 80x, it will be e power 80x. You can write all those things. The proof is clear. Okay. So that's all. This proves Stone's theorem. Stone's theorem. Okay. Now we want to prove another Stone's theorem, but I mean, which is the actual theorem. You want to take the derivative. It will be very short. I will finish it in 10 minutes or something. Okay. So this says that if you take a unitary group, there is a spectral representation like this, e power minus itx. You can represent it like that. Okay. Now, if you take the spectral unitary group, then we want to say that the derivative is actually given by the spectral measure. So this is the proposition, and this is the theorem. This is also called constellation. So let P be a spectral measure. Then and ut equal to e power minus epx, whatever it means, whatever the definition means, is a strongly continuous unitary group, and you take P to be Pf naught, where f naught of T equal to, I mean, so T is which is equal to integral T dpx, right? But this is unbounded operator, you have to consider domain and all that. T is an unbounded function and all that. Okay. This is equal to this. Then this is the statement. Then xi is in domain of T if and only if limit T going to 0, whichever way, T going to 0. I mean, I am usually used to this T decreasing to 0 because I consider semi-groups all the time. I don't consider group, so I wrote it. I don't have the negative part most of the time. So that's why I wrote that. So 1 by T ut u minus u exists. The derivative exists. Okay. So in that case, if u is in domain of T, then utu is also in domain of T. And what? And d by dt of ut equal to minus I ut of I minus I t, right? Minus I q, right? It is also equal to minus I t ut. Maybe I will write it there or yeah. Small comes with this. So theorem, we have already stated this theorem. We have used this theorem. Shall I erase it? Okay, is erasing is okay. Okay, the proof is simple. Okay. So this theorem is also in there. So proof is in. So suppose we want to show the derivative. Suppose U is the domain of T. T is nothing but Tn, right? That is U is in domain of T means T is defined to be this T dp, right? So T is in domain of T means that is integral x square d mu u, right? Is less than infinity, right? Mod x square or something. We use complex numbers. Here it's real, so it's okay. Huh? So this is smaller than infinity. This is what it means by T is in this. Now we want to use this and prove that we want to prove what the derivative is at 0. Okay. Now you take limit T from this. We want to consider the derivatives. We want to take the norm of 1 by T u minus u and minus the actual derivative. Actual derivative it, right? Plus 80 square. As it is, this is equal to this is the integral. Arm square I have taken. So this is the limit T going to 0. 1 by T e power minus itx minus 1 plus ITU. Okay. This mod square with d mu u by definition. Okay, this is by definition. This is what, because we have defined everything through spectral operator. By definition, it is this. Now notice that e power itx you get expanded. First term is 1, second term is this. First two terms are not there. Okay, so what we are going to have here is this is going to be summation n equal to 2 to infinity. When you divide it by 2 also, e power it power n equal to 0 to infinity n plus 1 into x power n plus 2 by n plus 2 factorial, right? That's what you are going to do, correct? Yeah. So you will have it a 1 plus n, 1 by n plus 1 will be n plus 2, which is less than or equal to half times e power minus itx. E power minus I half times. I can take t mod of this is mod t by time mod x square is not needed, x square times half of e power 1 by n plus 1 and 1 by n plus 2 is less than half e power minus I tx mod of this, which is 1 of course. Okay. This is true, which is e power itx, you can take it out and you get this. So this is less than this. Okay. Now we know that this integral is finite. So this integral is also finite. I mean, this integral is also bounded by this. Okay. So dominated convergence theorem will imply this goes to 0. I mean, what is this? This is going to be, you have a t term everywhere, but it's an infinite series. Okay. So you can't take the limit. So by LDCT, you have to use LDCT. Implies the limit equal to 0. This limit. That is the because we have norm x square, which is a bounded function, it's bounded by that. Okay? There is no t involved in that. It's true for every t. Right? No, you have a t which is the bounded function in t and which you can integrate. Okay, because of that condition. So it's all dominated by one single function. Yeah, near 0, you can even remove t. It's okay. This is less than even x square. Okay, so you have one single function and the measure is finite. Measure is a nice, I mean, it's finite with respect to that. So you can, also you can apply LDC and that goes to 0. Okay, so this was one way is proved. Now we have to prove the other way. This way. So suppose what u is in, suppose the limit exists. Okay? Limit t going to 0. 2t minus 0 divided by t exists. Okay? But then this limit is suppose this limit exists, then we want to prove that that integral is finite. That's all. We want to prove that it is in the domain. Okay? This is true for some u for u in, right? Suppose this limit exists, then we want to prove u is in the domain of t. That is, that condition is satisfied. Okay, so so this limit exists means what? This limit exists means that difference has to be. So this means limit of this. Let's consider without limit, which is just e power minus it minus 1 plus it this thing dv mu x. This is of course limit of norm square. Let's say limit of norm square. You can take the limit out inside for 2 systems. You can take the limit inside, right? Because the limit will go inside. The limit will go inside. And you have the same thing now. Okay. This is with mod square. That is the norm. Norm is mod inside, right? There is no norm. There is no norm. Norm is not there. There is no norm at all. It is just mod. That norm square is equal to the mod of this inside. Okay. Plus it. Okay. That is this mod of that inside. You take the limit inside, okay, of this e power minus itx minus 1 plus e power it. This okay. Now d mu. Now this is greater than or equal to. You have removed the first 2 terms. This is greater than or equal to. Okay. This is greater than or equal to. Greater than what? This is greater than that x square. No. So this is when the limit exists, this will be just itx square here. When that limit exists, okay, that limit. No, this is just a function, right? This limit always exists. Limit is equal to the limit. Correct? This square, mod square. You can take the limit inside the mod. This limit of this is just the derivative. Which is just, I mean, which are. You can. Or at least, I'm sorry. You don't need that. So I'm just taking only this. Okay, I don't. If I take -1 only, okay. Mod square. I'm just taking only the derivative. I'm taking this limit exists. Okay, you take the limit. Okay, this limit is same as this limit anyway. Here it is limit. It's not limit. This limit exists. This is just the derivative, and you have mod square, which is just going to be I x square. Right? It will be best. You will not have this, which is just equal to this integral it x square dv x. Okay? If that limit exists, this will be finite for each t. No, there is no t. T going to 0. It's just x. Sorry, so many questions. We just write it. I wanted to finish before time. I mean, after finish. So it will exist. Okay. And the rest is also easy. You just look at it, otherwise we will discuss in the next class. And next class I will have half an hour classes. Okay.